Let's illustrate this concept of environment types on different environments and different agents. So first of all, for the 8 puzzle, it's a fully observable because you could see the game at all the time. There is only one player, so it's a single agent. It's deterministic and also static. There's nothing going on around you, so there's no changes going on. And there's no chance random that things will change the course of your actions. And finally, it's discrete because there is a finite number of things you can do. So the descriptions are similar for chess, except that you have a multi-agent since you have more than one player. And you also have the environment can be either semi-static if you have a clock, in which case the score of the player will be actually decreasing as the clock ticks, or fully static if there is no clock. Concerning poker and backgammon, they are both actually stochastic because there is a chance to randomness happening by rolling a dice. So basically, they are both stochastic, not deterministic. They are multi-agent since you have more than one player. They are both static. The environment is not changing, and they are both discrete. However, poker is partially observable because you can see the cards on your hand's opponent, and backgammon is fully observable because you see the whole board and everything is really clear. Finally, if we take the example of self-driving car or taxi cab and also a Roomba, they are both actually continuous because they both evolve in a continuous space and time. They are both dynamic because what's going around is actually quite changing. So, there are other cars going on, there are other things going on in the room, kids playing, etc. They are both stochastic. For the vacuum agent or the Roomba, actually dirt can happen anytime. So the environment, it can be deterministic, but sometimes you could say that it is deterministic, such as in our small example of the simple vacuum word. For a car, it's multi-agent. For Roomba, it's single agent unless you decide to have several Roomba cleaning your house. And finally, they are both partially observable because you can see that next block or behind this big truck ahead of you. And for the Roomba, you can see under this sofa or what's going on in the next room. Actually, these environment descriptions are really not set in stone and depend a lot on how the task environment is defined. So this is just given as a reference, but depending on the kind of Roomba you have, the kind of car you have, and so on and so forth, these things can change a little bit. There are also 4 basic types of agents in order of increasing generality: simple reflex agents, model-based reflex agents, goal-based agents, and utility-based agents, all of which can actually be generalized to learning agents that can improve their performance and generate better actions. So first of all, what are simple reflex agents? These are agents that will select an action based on the current state, ignoring all of the perceived history. It's simple, but of course limited, because it can only work if the environment is fully observable. That is, the correct action is based on the current percept only. Simple reflex agents are illustrated with this diagram here that looks like the general diagram we saw earlier. So we have still environment, we have the agent, but in this case, we are going to use a condition action rule that will actually map each percept to the action it should do. To illustrate the concept of simple reflex agent, let's take again our example of vacuum, the simple world in which we have 2 rooms A and B, and the vacuum needs to figure out what to do. So the percepts are the location and the content that are detected by the location sensor and the dirt sensor. And the actions are going left, right, suck, or do nothing. So we have seen that actually we could write a table in which we have the percepts and the actions. For example, if A is clean, go to the right. If A is dirty, suck it, etc. Suck the dirt, etc. So let's start first by writing the function that actually does the vacuum cleaning. Let's call it vacuum agent. And this function will require to send 2 parameters, which are the location and the state whether it's dirty or not. And this function will actually return the action to do based on the table you have here. All right? So it's a simple if statement in which we have if the status of the room is dirty, then you're going to just suck, right? So, but in this case, we're going to return, since we are returning an action, we are going to return the action suck, right? Else means that the statue is clean. If we are here and the room is clean, we need to go in this next room. If we are here and the room is clean, we go to the left. So if the status is dirty, then if then we could ask if the location is A, then I'm going to return what? Return the actions of going right. Else, I'm going to return the actions of going left. This is a very simple reflex agent that just actually look up in this table and check actually which one of the actions is the most appropriate based on the percepts that it is perceiving, only one percept that is perceiving now. One question is whether if the vacuum agent is actually deprived from its location sensor. So what's going to happen? What's going to happen is that we don't have actually this values anymore. We just know that it's clean or dirty. So if it's clean, we don't know what to do, whether we should go right or left, because we don't know in which room we are. And this is the problem with the reflex agent, is that they are limited if they are partially observable. So in this case, the fact is that what we're going to happen is if we are already in the room A and we don't know actually what to do because we don't know in which room we are, and we ask to go actually left, then we're going to have loops happening here because we're going to be not finishing anymore. So if we're A and it's clean and we go left, 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 and same thing if we're in B and we go right, 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 so that's going to be a problem. So we're going to not avoid having this infinite loop if we have actually one of the sensors actually not working anymore. So a trick that we could do here is to turn actually this simple deterministic reflex agent into a randomized one, which means that when the room is clean and we don't know in which room we are, the agent could simply flip a coin and decide based on the coin what to do. So we're going to turn it into a randomized simple agent, and we decide between left and right by just flipping a coin. This is actually going to be better than a simple reflex agent that actually gets stuck in state and can't really move forward. Model-based reflex agents actually handle partial observability by keeping track of the part of the word it can't see now. It actually maintains what we call an internal state that depends on the percept history, which is actually usually a best guess of what's going on rather than an exact percept history. It models the word based on what? Based on two things: how the word evolves independently of the agent, and how the agent actions affect the word. So in this case, we're going to have a similar scenario in which we have sensors, actuators, what the word is like now, but we're trying to model the word as a state. So how the word evolves and what my actions will do will help define the model of the word. And then we still have the condition action rules because we still have a reflex agent, but in this case, we are maintaining a model of the word based on history of the percepts, which makes a big difference in terms of deciding what to do next. Goal-based agents are needed when knowing the current state of the word is not enough. The agents need something extra, and this something is some goal information. The agent program in this case combines the goal information with the environment model to choose the action that achieve that goal. So it actually considers the future with some questions like what will happen if I do A. So there is some thinking and deliberation instead of just checking a list of actions and reacting with a reflex. So in this case, we're going to think through different possibilities and then think about what would be the best choice to achieve the goal of the agent. It's flexible as knowledge supporting the decision is explicitly represented and can be modified. So in this case, we're going to have goals, and we're not going to have a simple, actually, lookup table, because it can be, such a lookup table can be really huge. Still, sometimes achieving the goal is not enough. We may look for a quicker, safer, cheaper trip to reach destination. Agent happiness in this case must be factored in and taken into consideration. We call it utility if you use the economics and computer science jargon. The utility function is the agent's performance measure. But because of the uncertainty of the word, a utility agent chooses the action that maximizes not simply the utility, but the expected or the average utility. So in this case, we're going to have, in the case of the agent, we're going to have the utility function that actually is here and assess how happy is the agent in such a state. And based on this utility, it will decide what actions to do through the actuators. So I've seen several types of agents, going from the simple reflex agent into utility agent. However, one could think that programming such agents can be very, very tedious, because you need, for example, for a reflex agent to enumerate all possible percepts with their actions, or you need to define a model of the world, which is not an easy task to do. So as Alan Turing said in 1950 in his famous paper, some more expeditious methods seem reasonable. We need to find something else. And this something else comes from learning agents. This generalizes actually all the previous agents we have seen. So a learning agent has 4 conceptual components, and these are, first of all, a learning agent, a learning element, and learning element is responsible for making improvements. This is what actually makes the agent learns from the past. A performance element is actually what is responsible for selecting external actions. It is what we have seen so far as agent. A critique is how well is the agent doing with respect to a fixed performance standard. And finally, a problem generator that actually allows the agents to explore different possibilities and learn on the go. Agent internal states can be represented in different ways. So we have the atomic representation, in which each state of the word is a black box that has no internal structure. For example, finding a route, driving route, where each city constitutes actually a state. So suppose we are in city A, city B, and we want to go to city C, right? What we want to find is the route between the two, and we don't care about the internal structure of city B and of city C. So we're going basically to just consider this as black boxes, and all we want is to go from a state to another one. AI algorithms that leverage this kind of representations are search, games, Markov decision processes, hidden Markov models, etc. A second way of representing the information is called factors representation, in which each state has some attribute value properties. So in this case, going from state B to state C, we have some information such as, for example, our GPS location, the amount of gas we have in the tank, and so on and so forth. And we have 2 states, B and C, that could actually share different characteristics. For example, these 2 have a flag on this second attribute. So it's an attribute value information that is added to the state. So this is a state. And actually the state, we know it as not only a black box, but we have information that are actually feature values or attribute value information. These are properties of the states. Artificial intelligence algorithms that leverage this organization include constraint satisfaction problems and Bayesian networks, to cite a few. In the third representation, called structured representation, relationships between the object of a state can be explicitly expressed. So we have a state A and a state B. And actually, each of the states not only have attribute values that describe the state, it has also a relationship between the objects. For example, pedestrian crossing the street, so there is a relationship between pedestrian and street, etc. So AI algorithms leveraging this kind of structure include first-order logic, in which you have a relationship between objects, knowledge-based learning, natural language process, understanding, etc. So we went through several concepts today. We went through the concept of rational agent, the concept of different types of environment, different types of agents, and also the different types of representations of states and agents. So I would like to conclude by saying that the concept of intelligent agent is actually central in artificial intelligence. AI aims to design intelligent agents that are useful, reactive, autonomous, and even social and proactive. An agent perceives its environment through percepts and acts through actuators. We also saw that there is a performance measure that evaluates the behavior of the agent. An agent that acts to maximize its expected performance measure is called a rational agent. We also saw that we can define different criteria for rational agent environment, and this is called P's, a task environment specification that includes performance measure, environment, actuators, and sensors. We also saw an important aspect that actually an agent is a set of architecture or hardware plus a program or system, and both have to be compatible to work together. We also saw 4 types of agents: reflex agent that are the simplest ones, model-based agent that try to model the word by creating the model internally, a goal-based agent that want to model the word but still have a goal to achieve, and finally utility-based agent that try to increase their happiness. Agents can improve their performance through learning, which is a central piece today in AI that actually aims to make the agent aware of different situations and learn from its experience. So this was a high-level representation of the different agent programs. We have seen lastly that state representation can be either atomic, factored, or structured, which goes by increasing order of expressiveness. Finally, I would like to finish with this beautiful diagram that actually shows the roadmap for the next lectures in AI, our next lectures in AI. That shows the roadmap for our next lectures in AI. And this includes actually, on the axis here, we have the level of intelligence, which is also the expressiveness power of the AI agents. So we have first the reflex agents, and we saw that reflex agents are very simple. They have a lookup table that has actually percepts and has actions. And all that the reflex agent is doing is pick the, for a given percept, pick the action corresponding to that percept. So this is considered as a low level of intelligence because there is no much thinking of deliberation about what to do. Just look up this table. It can be actually very big and decide what to do. We have seen that we have seen that state representation could be atomic and could be considered as a state in which it's a black box. And this includes search problems, such as finding a route, or Markov decision processes, or games. We also have seen the factored state representation, in which we have variable describing the state, and this includes problems in constraint satisfaction and Bayesian network. And finally, we have seen the state where we have an increased level of expressiveness that are structured in logic, in which we have actually more information being encoded in the state that actually includes the relationship between the different objects describing the state. Finally, machine learning provides a set of techniques and methodologies that can produce agents that go across all of this kind of level of intelligence and expressive powers. So you could have, for example, a spam filter that could tell you, predict whether a spam is an email is a spam or not. That would be a reflex agent, and the complexity could go, and the expressiveness of the knowledge discovered by machine learning algorithms could go as high as logic expressions and first-order logic, and also natural language processing. So this was it for intelligent agents today. Next time we're going to start the topic of search and games, so in which we model the world with states that are black boxes, and this includes search problems and adversarial games.